Hi all, in this video I want to get into, I think, the trickiest part about inverse functions. So actually, I think surprisingly, quadratics give us a lot of trouble. So the cubics and the cube roots and the rationals, they're all fairly well behaved. But when we try to find the inverse of a quadratic function, one of the functions we've been working with for the longest and are hopefully the most comfortable with, we get into some trouble. So, I'm going to work with f of x equals x squared minus 4x, and I want to start right off with trying to get a picture of what this thing looks like. So let's see. You could complete the square if you want to do this using transformations, but we can use other tricks as well. If I factor out an x, I can see that this thing has x-intercepts at 0 and at 4. That means the vertex has to be right in the middle at x equals 2. Parabolas have some symmetry, so if you know your two x-intercepts, the vertex will always be directly in the middle. I can plug the x equals 2 back in, and I get 4 minus 8, so negative 4, which means this is my vertex. So I think this is a good sign. It was looking like something that should open up, and that's what I'm seeing here. I'm even going to snag a couple more points. If I plug in 1, I get 1 minus 4, negative 3. If I plug in 3, I get 9 minus 12, which is also negative 3. And then if I plug in negative 1, I get 1 plus 4, which is 5. So I should also get a point over here at 5, 5. So there are more points, but those are all the points with nice integer coordinates that fit into the grid that I provided. Okay, so there is a fairly good picture of y equals f of x. So the first thing that I want to try to do is sketch the graph of f inverse of x. Let me see if I can find a color that's working here. Okay, so if I want to sketch the graph of f inverse, that means I need to flip the graph of y equals f of x over the line y equals x, which means every point on this graph is going to have its x and y coordinates switched. So starting with negative 1, 5, my inverse should go through 5, negative 1. 0, 0 actually doesn't move when I flip across y equals x. Neither does 5, 5. What is this one? 1, negative 3 will land at negative 3, 1. 2, negative 4 will land at negative 4, 2. 3, negative 3 will land at negative 3, 3. Am I missing anybody? Yeah, 1. 4, 0 will land at 0, 4. Okay, so big thing here is those are the points, but what I'm doing is picking this thing up and flipping it diagonally, which means what I'm getting is a sideways parabola. Okay, so here is what is supposed to be the graph of my function and what I would like to be its inverse, but I'm not happy about it. I'm going to put a question mark there. I don't know if you spotted this right away or not, but I hope that you will spot that there's a problem because what I've drawn and claimed should be f inverse is not a function. It doesn't pass a vertical line test. So this is no good. We would actually do something that seems very dramatic, but we'll fix it in a minute. We would say if you start with a function and you try to find its inverse and what you end up with is not a function, then the thing that you started with is not invertible. So here I would conclude that f is not invertible. I will backpedal in a minute. We won't just give up on this f completely, but as it stands, this function is not invertible. So what we need to do is figure out how we could look at the graph of the function in the first place and figure out that its inverse, its proposed inverse, was not also going to be a function, and then we can try and modify the function to fix this. So basically, I've drawn this. Here's an example of a vertical line at x equals negative 2 that crosses the proposed inverse more than once. If I wanted to just look at the original function and see that that was going to happen, remember x's and y's switch. So if this is x equals negative 2, then on the original function, that should be giving me the same information as a line at y equals negative 2. So in order for a function to be invertible, it has to not only pass its vertical line test, that's what tells us it is a function in the first place, but it also has to pass a horizontal line test so that its inverse will pass a vertical line test. So basically, every input needs to have exactly one output, and the reverse now also has to be true. Every output has to get paired with exactly one input. So we need unique input-output pairs. No x is repeated on the function and no y is repeated on the function. So I've summarized some of this here. Back to our problem. We don't want to just give up on this quadratic function. We use them all the time. So what we can do is we can look at part of the quadratic at a time. So we can split it, and we try and split it in a way that we keep all of the y values that this function hits, if possible. It's not always possible, but here I can. If I split at the vertex, I'll make sure that I hit every y in the domain of function f without repeating any. So I would either choose the right-hand side or the left-hand side. Each one of those should give me an inverse. So basically, if we deal with f in two pieces, we can get inverses for each part of the function. I'd like to look at the left-hand side. So let's see. I'm going to define a new function. It's not f anymore. The function and the domain are inseparable. So this is no longer function f, but it looks just like function f up until x equals 2, at which point it dead ends instead of continuing on for x greater than 2. So that pink section right there on my graph is what I'm looking at. And I can sketch the inverse, but I would like to work on the algebra first. So if I want to look at y equals x squared minus 4x and algebraically find its inverse, I'm going to say x equals y squared minus 4y. This is a little tricky. We want to solve this for y, and it's quadratic. So we have two choices. We can either use a quadratic formula or we can complete the square. I'm going to show you the complete the square, but let me just say, if you like the quadratic formula option, go for it. But you first have to set this thing equal to 0. So a little bit of a side note here. Y is your variable. So when you go to use your quadratic formula, you're going to use a equals 1. You're going to use b equals negative 4, and you're going to use c equals negative x. X is not your variable that you're solving for, y is. So you actually have to put that x in your quadratic formula, which ends up being a good thing. It will give you a y equals, and it's supposed to be a function, so it should have an x. I like the way the complete the square works on this, so let me actually walk you through that. But if you want to work through the quadratic formula, you should get the same thing. It might be off a little bit just on some simplification, but it should give you a valid formula. Okay, so complete the square. This is actually beautifully set up. I want to figure out what to add to y squared minus 4y to make a perfect square, which means I need to take this number right here and cut it in half, which will give me negative 2, and then square it, which will give me 4. Okay, we can't add 4 only to one side, so we add it to both sides, and now we have x plus 4 equals, we can factor the perfect square. This should be y minus 2, y minus 2, so y minus 2 squared. And now it's much easier to solve for y. I have one y on one side of the equation, so I just need to get rid of the minus 2 and the square. And I'm going to do that in the opposite order. So first get rid of the square, which means I'll get a plus or minus the square root of x plus 4 equals y minus 2. And then I'm going to add 2. So plus or minus the square root of x plus 4 plus 2 is equal to y. Okay, I'm not going to name this f inverse yet because I have the exact same problem I had with the graphs. With that plus or minus in front, that's not a function. If I pick an x value, I'm almost always going to get 2 different y values. So that's not good. So again, telling me exactly what the picture was telling me. But now I can go back up to the picture and I can say, all right, well, I already narrowed this down. I'm only looking at this half of the f of x function, and we should be able to pair that with either the top or the bottom half of this f inverse that we proposed early on. So the vertex is definitely going to be included. We're keeping the part of the graph that has 1, -3, so we should be getting through -3, 1, and 0, 0, and -1, 5. So we're keeping the bottom half. To get the bottom half, we need the negative square root. Thinking transformations, if we put a negative in front of our square root, it flips it over the x-axis, and that's exactly the shape we're getting. So when we looked at this picture and we got sideways parabola, really what that was a positive square root function and a negative square root function, 2 square root functions. And once we split the function in half, we can choose the appropriate one, the positive or the negative, to go with our half. If we had chosen the right half of the original function, we would get the positive square root graph. I think pictures are really powerful for finding this. Okay, so what did we say? We said that, who is this? G inverse of x is the negative square root x plus 4 plus 2. If you want a little bit of a shortcut, if you aren't being asked to graph the function in the inverse for the problem anyways, you can avoid that by thinking domain and range. So it really does come back to the picture still, but you can do some of that in your head. So if you can kind of figure out what this original function looks like, we can say, okay, and again, I'm talking about G, not F, so just this half. So G, the domain, is x less than or equal to 2, that's given. The range is y greater than or equal to -4. Those should be flip-flop for the inverse, so this is a really good check as well. The domain of this function should be x greater than or equal to -4, just based on looking up here, and that absolutely matches what I'm seeing on my equation, because I would want x plus 4 to be greater than or equal to 0, so I could take its square root, which means x greater than or equal to -4. So those two are verifying the fact that I've done this correctly, since they agree. If my domain up above is x less than or equal to 2, so this thing provided, that means down here my range should be y less than or equal to 2. If you want your y to be less than or equal, you have to have a vertical flip. Square root functions are generally increasing. So if we want to have it only give us y value smaller than 2, it has to be an upside down square root. It doesn't matter if it's flipped once or flipped twice, but we have to have a less than or equal to. So again, if this is a less than or equal to, you're going to choose a negative root. If this is a greater than or equal to, you're going to choose a positive root. Okay, so there's a little bit more trickiness. That wasn't actually the end of it. If that wasn't enough, there's a little bit of trickiness in the checking as well. So we'll check this one both ways. It's a little messy on both parts, but one I think is trickier than the other. So we're claiming, where do I have it? There they are, that our function is g of x equals x squared minus 4x, and its inverse is negative square root of x plus 4 plus 2. So if we want to find g of g inverse, that means we're going to plug in this negative root x plus 4 plus 2 into our original function, which will give us a negative root x plus 4 plus 2 squared minus 4 times negative root x plus 4 plus 2. Unfortunately, the inverse operations, because of the way these two are written, aren't bumping right up against each other in our order of operations, so they don't just cancel out as nicely as we might like. They will cancel out, but the algebra involved is a little bit messy. So what we actually have to do, it might seem like a terrible plan, but it will work out nicely. We have to multiply this thing out. So we have to deal with the power, which means multiply this thing by itself, and we'll have to FOIL that. So the first is nice, negative square root of x plus 4 times itself. The negatives will wipe each other out. When we square a square root, that also wipes each other out. So all we're left with is the x plus 4. My outside, not so nice, but not too terrible. I get a negative 2 times the square root of x plus 4. My inside gives me the exact same thing, a negative 2 times the square root of x plus 4. It would be delightful if those two had opposite signs, but they don't. And my last gives me a plus 4. Okay, and then I also have to deal with, so that was just this first set of parentheses, distributing through here. So first the negative 4 multiplies by the negative root x plus 4, and that gives me positive 4 square root x plus 4. And then negative 4 times 2 is a negative 8. And that was a little bit messy, but it is doable as long as you recognize the FOIL here. We know how to FOIL things out, so just don't be put off by the fact that it looks a little messy. When we go to collect all these terms, this is when finally some nice things start to happen. I have a 4 plus a 4 minus an 8. That is all gone. I also have negative 2 times the square root minus another 2 of that square root. So this is negative 4 square root of x plus 4. And then I add a 4 square root of x plus 4. So those also drop out. So toughing it through one really messy step does give me that g of g inverse of x is equal to x. I did ask for a domain restriction on this. This won't necessarily be true for every x value you choose. Some x values are not valid to plug into g inverse. So the domain restriction should be the domain restriction of the inner function. X has to be greater than or equal to negative 4. Okay, so that one was a little messy. The other one is also tricky. In some ways, I think trickier, but I love it because something really cool happens if you're paying close attention. So g inverse of g of x. G of x is an x squared minus 4x. If we plug that into g inverse, right up here, we're going to get negative square root of our input, x squared minus 4x, plus 4. And then there's a plus 2 hooked onto that. Okay, so this looks kind of messy, but one really convenient thing is that this factors and is actually a perfect square. So we get negative square root of x minus 2 squared plus 2. Okay, so we need to be really careful, but I'm going to go with what I would usually see happen next. So usually what I would see is, okay, we're squaring and then we're square rooting. Those two are inverse operations, which is true. So we get negative x minus 2 plus 2. If someone's being not careful, they'll lose this negative sign, which actually makes it look like things are working out beautifully. But if you don't lose that negative sign, you get a negative x plus 2, which does not equal x. Okay, so first I want to catch you on that because that's what most people will do. We actually did something somewhat illegal. We need to go all the way back up to here. The truth is, when you take the square root of something squared, you don't always get exactly what you started with. If you started with a positive number, then you'll absolutely get back exactly what you started with. But if you started with a negative number, you square and square root, you end up with a positive number. So what you're really getting here, cross these off, is negative absolute value of x minus 2 plus 2. Which probably doesn't immediately make you feel any better because it still doesn't look like I got x, which is what I should get if these are inverses. Oh, sorry, I'm getting off the bottom of the page. So there we go, negative absolute value of x minus 2 plus 2. Here's the reason I think this is really cool. For starters, I love that it catches us on this absolute value. We don't talk about that a lot. If you take the square root and then square, you'll get back what you started with, but you're only allowed to start with negative things. You're only allowed to start with positive things. If you square and then take the square root, you'll get back what you started with if it's positive. You are actually allowed to plug in things that are negative to a square and then square root, but you won't get back the same thing. You'll get back the positive version of whatever you started with. Okay, so back to, we were hoping to get y equals x. Why did we not? Here's the deal. What we got is an absolute value function, and it's been flipped upside down, and then we've taken it and we've shifted it right to and up to, so it looks like this. 2, so this is right at 2, 2. And then we have to be a little bit careful because this does have a domain restriction. The domain restriction should come from the original function g of x. And if you look back, we defined that g of x was only half the parabola. It was the half for x less than or equal to 2. So looking back at this graph, if x has to be less than or equal to 2, we can cross out all of this, and we really only end up with this piece, which in fact is exactly identical to y equals x. So the algebra kind of failed us there, but if we think about graphs, we really did get what we're expecting. So I think that one's pretty cool because it looks like we got in big trouble, but actually we're right on. All right, thanks for watching.